Hi, this talk is about an accumulative model for quantum theories. I'm going to give a new way of looking at quantum mechanics and at the nature of reality in general. So, first question, why must time be the dynamical variable? Now, what am I referring to here? Ever since the time of Galileo, and even before, the equations of physics have been phrased as equations where physical quantities vary as functions of time. Consider, for instance, Newton's second law, F equals ma. All right, F, let's see if we can get this working here. F equals ma. All right, so what does A mean? A is simply the derivative of position, it's often written as x, with respect to time. So the position evolves as a function of time. Now that's typical physics, but does it have to be that way? Do we have to have physical equations in which everything depends on time? Well, there are equations where this is not the case. Consider the principle of least action. Let me see if I can draw this. So what the principle of least action says is that if I start at a point at a certain time, so I'll just schematically represent this as x0 at time 0, and I want to know how it can get to x1, t1, then the path that it follows is the path that minimizes the action. Now, I'm not going to go into what action is, but there is a certain quantity action that you can define as a function of different paths. And the path that gives the smallest value of the action turns out to be the path that the object actually goes from if it goes from position x0 at time t0 to position x1 at time t1. Now notice this picture does not really show a system evolving as a function of time. It fixes the beginning point, it fixes the end point, and it says, explains what happens in between. Now let's compare this to another process, for instance, the relaxation of a cable. If we have a cable that's fixed at two endpoints, and the cable has a certain length, then if you attach the cable here and here and then allow it to hang, the shape it's going to take is going to minimize the potential energy. Okay, so here we have a process by which when the 2 points are fixed, the path in between is determined by a certain process. I mean, the cable will settle down and eventually all the motion will stop and it will hang in a stationary way, connecting the 2 points. So in some sense, there seems to be a similarity between these two situations. It seems to indicate some sort of process of relaxation that does evolve in time. So perhaps the principle of least action reflects some kind of process. But this process can't be a process that evolves in time because you're fixing the time at the beginning and at the end. And then you're getting a path that involves all the times in between. Now, where does the principle of least action come from? Well, you can trace it back through the principle of stationary phase, what Feynman called. And this principle of stationary phase is related to the notion of a path integral. Now, what is a path integral? Let me try to write in a very simple way. I can consider it as a sum. There's a sum over paths. And you can think of paths as in the same sense as paths in the previous slide. And these are certain paths gamma. You use the symbol gamma typically, which are contained or which belong to a certain configuration or certain event A. And then we're taking the e, the exponential function, to the I times s of gamma. All right, this s looks like a delta, but this s is the action. So every path gamma has an action associated with it. And we're summing over all paths that are associated with a particular configuration. Okay. Now, this path integral itself is not physically measurable, but if we want to get the probability of a certain configuration is proportional to the path integral squared, absolute path integral squared. Okay. So the path integral is really a fundamental mathematical object that determines probabilities, and quantum mechanics is based on these probabilities. Okay, so this expression here, where you're summing over exponentials, complex exponentials, where the argument of the complex exponential depends on the action, this expression is fundamental, really fundamental to all of quantum mechanics or quantum field theory. Okay. Now, what does this expression suggest? Now, to a physicist, if you take off the I, then this looks very much like a partition function. And that was the motivation for Euclidean quantum field theory, which has been a very fruitful means of investigating quantum field theory. However, a communications engineer sees something different. He sees what I would call multipath. You have the path gamma. This S talks about the phase of the signal as it passes along that path. And then as the signal wiggles, this gives the amplitude. When you sum up, you're summing over all signals that end up at a particular point. So I'm going to take this second point of view and try to compare this partition function, this path integral, to a multipath conception. Let's see where we can go with that. Okay, so I'm going to give what I call a cellular scenario. And I'm doing this to introduce concepts and kind of get your mental framework that we can compare, and then afterwards I'll draw an analogy. Okay, so I'm sure you're familiar with cell phones, so let's consider a case where you have a cell phone tower, okay, transmitting signals, and you have someone with a cell phone out here somewhere, so I'll draw my cell phone like this. And this person is moving around in a random way. Okay? All right, now, as he moves around, the signal is the base station, the tower, is transmitting signals. Now, these signals, some of them travel in straight lines and will go straight to the cell phone. Some of them will bounce off various objects like trees, houses, and so on. And these bounce signals will also come to the cell phone. So the signal that hits the cell phone is going to be a sum of all of these signals. And this sum has exactly this form that we talked about, exponential I times what I can call the phase difference, which depends on the path. And here we're summing over paths. And actually, there would be an amplitude out here, but I'm not going to consider that at this moment, just this simple picture. Okay, now as this cell phone moves around in the space, so follow some path, it's going to accumulate this signal. And the signal sometimes will be stronger, sometimes will be weaker. Now the cell phone becomes aware of the signal when the accumulated signal reaches a certain threshold. So we have an accumulated signal which reaches a threshold. All right, now the question is, where will the cell phone be when the signal reaches the threshold? So that's the question. Where's the location? The location of detection. Okay. Now, since the cell phone is moving randomly, we can't tell for sure, but we can give some idea of the probabilities. It turns out that the probability of the cell phone being at any particular location, okay, the probability, say, for instance, that the cell phone is here and the detection takes place at that location is proportional to the absolute value of the sum over the, sorry, didn't my gamma sideways, sum over the paths squared. This is exactly the same expression that occurs in quantum mechanics. So let me recap again. The tower is transmitting a signal. The signals bounce around, creates multipath. The cell phone moves in this field of signals. At each point, it accumulates the signal and continues to move. And when the accumulated signal reaches a certain threshold, then we say that there's a detection. The probability of the detection occurring in a particular location is proportional to this path integral expression, absolute squared, just like quantum mechanics. Okay, so the reason I shared this picture was I want to make an analogy. I suggest an analogy between this picture and the quantum mechanical nature of the universe. Okay, so the cell phone, I'm saying, is a representation of all of reality. Okay, and this is not just the reality that we see, the universe that we see, but the dynamics that lies behind what we actually see. Motion, I would call this a non-space-time process. Now, in my cell phone example, I found probabilities of locations of detection. Now, in the real world, we're not just talking about the probability of locations, but we're talking about space-time events. So just as in the example I gave of principle of least action, the principle of least action can't come from a process that evolves in time because it involves fixing points in space-time and finding a path between them. In the same way, if I want to talk about the dynamics of the universe in this way, in this analogy, I can't say it comes from a process that occurs as a function of time because time is one of the variables that's being determined. Okay, so the motion of the cell phone in my example is representative of a non-space-time process. Okay. The signal detection, as I said, the moment where the cell phone detects the signal, I call that the universe as we know it. The configuration at that moment of detection is the configuration of the universe that we experience. So what I'm saying is behind the reality that we experience, there's a process which is not in space-time. It does not involve space and time. It occurs, it evolves, it develops. While it's developing, a signal or some such similar conception accumulates, and when a threshold is reached, then we attain the universe that we experience around us. Okay. All right, now, what's the payoff from this way of looking at quantum mechanics? Well, first of all, it does give you, naturally, the quantum expression for probability. This is a very unusual way to get probabilities. And you find probabilities all the time in physics and technology. But the quantum expression for probability is a very unusual one. The model that I've given gives a natural way which explains why the probability has this form of expression. Okay. This way of looking at reality resolves all quantum paradoxes. I'm not going to go into all the different paradoxes of quantum mechanics, but there are many. But this way of looking at reality resolves all of them. Why? Because it explains at the base the fundamental mathematical formalism that underlies quantum mechanics. So if it explains the mathematics, it fits the mathematics, then it's going to explain all the paradoxes that result from the mathematics. Okay. For instance, there's one to talk about the collapse of the wave packet. People have talked about this ever since the beginning of quantum mechanics, that when you observe something in an experiment, then what seems to be a continuous wave, suddenly collapses into a single point. And that doesn't happen in the model that I've presented, because the collapse, as it were, is simply occurs when the universe is manifested. At the point of accumulation, at the point of detection, that determines the universe. There's no collapse. It's simply that there's been an accumulation behind that detection, and the detection is actualized at a single point. So this continuous wave function, this continuous distribution, is an artifact of the process that's occurred before the universe is actualized. There's the modern picture of the vacuum is as extremely complex, a bubbling brew of particles and antiparticles. In the picture that I presented, that whole bubbling brew disappears. It's a vestige of the process by which the universe is actualized. As the cell phone, as it were, wanders, it encounters a various of configurations, a variety of fields, but at the end, it's a single configuration, single field. So the reason why it seems that the vacuum is such a complex structure is that we're looking at vestiges of the process through which the universe has finally been formed. Okay, one of the more and more popular views of quantum mechanics is the many worlds theory, which requires that the universe branch at every instance into enormously, exponentially growing set of parallel worlds. Now, the picture that I presented completely demolishes the need for this kind of branching. In physics language, I can say that the state space in the picture that I've presented is far simpler than the state space in the many worlds theory. Okay. The picture that I've presented does involve physical predictions. Since I'm saying that the quantum probabilities are the result of a statistical process, then there will be some variations due to the statistics. In fact, the prediction is that for events or configurations that have larger probabilities, the probabilities will be slightly reduced because of these statistical effects. And small probabilities, or probabilities that are theoretically zero, will have some slight probability due to statistical fluctuations. Now, unfortunately, I can't predict the size of these fluctuations. This is similar to the situation in molecular theory, where we know that the motion of molecules produce fluctuations, Brownian motion, and so on. You can't predict the size of the Brownian motion. The Brownian motion depends on the size of the molecules, and the only way to see the size of the molecules is to measure them. You can't predict that a priori. But there is this prediction that probabilities will be slightly different from the quantum theory because of statistical effects. I have worked the mathematics out in some detail. It appears to work, and I invite you to read this article. And thanks for listening.